Greetings. So, we will begin a new unit today. This will be on spectroscopy, and in particular what is called as Stark spectroscopy, the Stark effect, and also the Zeeman spectroscopy, and we will deal with various aspects of this. So, I would like to begin with a comment on the symmetry of the Hamiltonian, because it plays a central role in getting the eigenstates of any quantum system. Now, quite often the problem in quantum mechanics is quite complex, especially when you are dealing with larger systems. If you are dealing with molecules or clusters, bulk matter and so on, the quantum mechanical problem is quite challenging. And what you can do is to exploit the symmetry of the Hamiltonian, because if you have an operation which leaves the Hamiltonian of the system invariant, like you have an object like this, and if you rotate it through an arbitrary angle about its axis of symmetry, right, then you have a rotational symmetry about a certain axis, but not about every axis, and sometimes this symmetry can be through rotation through a finite angle or through an infinitesimal angle. It could be reflection, it could be a combination of reflection and rotation and so on. So, if you have a symmetry operator R, and there are a number of symmetry operators like R1, R2, R3 and so on, and if you stack them together, and let us say there are h number of such operations which leave the Hamiltonian invariant, so that for every I the Hamiltonian commutes with the symmetry operator, it remains invariant. Then these operators which have been stacked together in this set, which I have called as G, is what is called as the group of Schrodinger equation, and this is very advantageous because since these two operators commute with each other, they can be simultaneously diagonalized, and you can get simultaneous eigenstates of the two operators. Okay. So, which means that if you want to find the quantum eigenstates of the system, instead of solving the quantum mechanical problem, you solve the mathematical geometrical problems from group theory, and those solutions will give you a basis of functions amongst which you can search for the eigenstates of the Hamiltonian. So, the problem in quantum mechanics benefits from converting that at least partially into a problem in mathematics, in group theory or geometry. Okay. So, that is the big advantage which connects group theory and quantum mechanics, and my favorite reference for this is Tingham's book Group Theory and Quantum Mechanics, which I strongly recommend. And since we are now dealing with a group of Schrodinger equation, if you have these two operations Ri and H which commute, then their ijth element of this commutator would go to 0, okay, the ijth element of the commutator. This is the ijth element of the matrix representation. Okay. So, you can have a matrix representation in a certain basis, and you can, if you solve the geometrical problem, you get the eigenstates of the symmetry operator, and in the eigenstates of the symmetry operator the matrix representation of the operator R will obviously be diagonal. Okay. So, now you construct an eigenbasis of the symmetry operator. These are not necessarily quantum mechanical eigenstates, okay, but these are eigenstates of the symmetry operator in which the symmetry operator is diagonal, and if you use the fact that the ijth element is 0, then necessarily it means that if you sum over Rik Hkj minus sum over k Hik Rkj, then this sum would vanish, but R is diagonal. So, Rik will implicitly include a Kronecker delta, it will be non-zero only if I is equal to k, and here because of this Kronecker delta delta Kj, this element rkj will be non-zero only if k is equal to j. So the summation over k will contract and you get rii hij minus hij rjj equal to 0, and now you can factor out hij as common and you have this product which vanishes, which means that if one of the factors is not 0, the other must be 0. Okay. So that is the comfort we get, that you do not have any off diagonal elements which connect functions of different symmetry, and this provides tremendous advantage in getting the quantum mechanical eigenstates of a system. And this is a feature that we will exploit when we look at the Stark effect, because this is related to the question of degeneracy. You can see how it is related to degeneracy, because if you have psi n which is an eigenfunction of the Hamiltonian, and then if you operate on the Schrodinger equation by a symmetry operator p, then p, so I have simply taken the Schrodinger equation and I have p operating from the left on both the left side as well as the right side, and on the left side you know that p and h commute, so h can now be written behind p, and on the right side E is a constant. So you find that the state psi n and the state p psi n are essentially degenerate, okay, which is why the symmetry of the Hamiltonian, whenever you have a symmetry of the Hamiltonian, you have degeneracy, and you can break the degeneracy by applying a perturbation if the perturbation Hamiltonian has got a symmetry which is different from that of the unperturbed Hamiltonian. Okay. So in Stark effect you break the symmetry of the Hamiltonian by applying an electric field, and the Zeeman effect you use the magnetic field. So the degeneracy can be removed by breaking the symmetry of the Hamiltonian, and you may break the symmetry either partially or fully, and then you can look for spectroscopic transitions between the states of the full Hamiltonian, which is the unperturbed Hamiltonian plus the perturbation Hamiltonian. Okay. So you can have transitions between that, and this is what Stark spectroscopy and Zeeman spectroscopy is about. So the first experiments were done by Stark in the early part of the 20th century, and he examined the spectrum in of atomic spectra in electric fields. So let us consider the hydrogen atom placed in an electric field now. Now let us say that the electric field is applied along the z axis, and if you now plot the potential seen by the electron, it is the Coulomb potential, which you know goes like this, right. It is -1/r, but I am plotting it as a function of z for a given value of x0 and y0, for a given value of x equal to x0 and y equal to y0, so which are finite. So it does not go to -infinity, it goes to it cuts the vertical axis, the potential axis over here, because at z equal to 0 the denominator is not 0. Okay. So this is the Coulomb potential that you have, this is plotted as a function of the z axis, and in addition to the Coulomb potential which is generated by the proton nucleus, you have the applied electric field which is a linear field. Okay. So this will have a linear interaction which is charge times the electric field, and then you have got this EEZ, this is the interaction Hamiltonian of the charge in the presence of the electric field. So now you have the unperturbed Hamiltonian, for which the Schrodinger equation solutions are well known to all of us, these are the hydrogen atom solutions, and then the problem you are dealing with is that of the full Hamiltonian, which includes the unperturbed Hamiltonian plus this which is a perturbation. Okay. So we are going to use perturbation theory, which you have done in your earlier course in quantum mechanics, but I will review some of the more important parts of that for the sake of completeness. So you have we will deal with the spin later. So we will deal with the non-relativistic Schrodinger equation and its solutions, where the eigenstates are given by the quantum numbers n, l, m, which are good quantum numbers in this situation, and the perturbation is E E Z. This script E is the electric field, this little e is the electron charge, and let us consider the ground state of the hydrogen atom and use the result of the first order perturbation theory, from which we know that the first order perturbation correction will simply be the matrix element of the perturbation Hamiltonian in the ground state, right. So all you have to do is to get this first order correction, and what will this turn out to be? This is the 1s state of the hydrogen atom. This has got a symmetry of the z axis, right. So this has got a parity which is odd. This state this state as well as this state both have got even parity. So this integral will essentially vanish, because the contributions of the plus z will cancel the contributions from the minus z when you take the integral over the whole space, right. So this integral vanishes, and essentially what we find is that there is no Stark effect at all. It does not change the ground state energy of the hydrogen atom. If you keep it in an electric field, its energy is not going to change, okay, because the matrix element in the first order at least does not contribute anything. Now so far so good. What about second order perturbation effects? Okay, in the first order we do not have any correction. What about second order corrections? And there may be some, so let us not assume that they also vanish, and in fact they do not. So let us look for the second order correction, and the second order correction is given by this term according to the perturbation theory. So this I am sure you would have done in your earlier course in quantum mechanics. So I will use that result straight away, and this is the result of the second order correction, and you can already see that it will not be 0, okay. It will not be 0. You need to sum over all values of n. So this is your hydrogen atom bound state spectrum, everything converging to the Rydberg series limit at e equal to 0, and then this even minus En for n not equal to 1 will be non-zero, and then you have got non-zero terms elsewhere. So this will give you a non-zero correction. Now this is the correction that we need to estimate. So let us see how to do that. First thing to recognize is that the ground state will certainly be lowered, because here these are squares, so they will be necessarily positive. Here in the numerator also you have got a square, so the sign of this entire sum will be determined by this sign, and even is the lowest state. So even minus En will be negative, and this will have a negative sign. So the energy of the ground state will be lowered by second order correction. So that is the first thing we know, at least at a qualitative level. So let us extract this minus sign. That is all we have done in this step. So the denominator is written as En minus E1 instead of even minus En, and this is of course different for different values of n. The denominator is different, but notice that this En minus E1 denominator, this difference will become larger and larger as you go to higher values of n. So let us take the least value that is possible, and that is for n equal to 2, okay, and that means that you get a certain bound which guarantees that this second order correction will be greater than this difference, in which you have extracted 1 over E2 minus E1 outside the summation sign, okay. So this is a certain bound that you get, and now what we want to determine to get this bound is this summation over all values of n going from n not equal to 1. So it will go from 2 all the way up to infinity, and then of course you need to sum over corresponding values of L and M as well. So this is the quantity that you want to determine. So let us see how we do that. So to get this summation, but we do not want to include n equal to 1, but how does it matter? We can also include n equal to 1, because we have already found that if we did include n equal to 1, it contributes 0. So you can always add a 0 to an entire sum. So we can extend this summation, which was from n not equal to 1 to infinity, to include n equal to 1 to infinity. Okay? So we need not restrict n not equal to 1 anymore, because what it is adding to the total sum is only a 0. So this is the summation that we want to get, and this is the modulus square. So this is the product of the matrix element of Z times the complex conjugate of this, and now you recognize the advantage of extending this sum to include n equal to 1, because that is what makes this what is sandwiched in between a unit operator, that is the resolution of unity. Okay? And that is possible because we have included the n equal to 1 state. So we recognize the resolution of unity, and we find that what we are looking at is essentially the matrix element, not the product of the matrix elements of Z, but actually the matrix element of Z square. So there is a Z to the power 1 here and a Z to the power 1 here. So that gives you Z square. So the sum over all states of this modulus square of the matrix elements of Z is equal to the matrix element of Z square itself. And that is not very difficult to determine, because so far as the hydrogen atom in the unperturbed state is concerned, it is completely symmetrical and it does not recognize any difference between x and y and z. So there will be an exactly identical expression for x square and y square as well. So this will be 1/3 of r square. Okay? And the average value of r square, the expectation value of r square, can be very easily determined for any eigenstate of the hydrogen atom, which is for n equal to 1, it is a0 square by z square. Okay? So now we have this result, a0 square by z square, and we have found the quantity that we needed. This is the a0 square over z square that we have found, and using this a0 square over z square, we find this bound, which is the second order correction to the ground state of the hydrogen atom due to the Stark effect, will be certainly greater than this quantity over here, which is 1 over E2 minus E1, and you know what E2 minus E1 is, so you can find that out. Okay? So all you do is to plug in the numbers and you can get this. Now there are some other consequences of this, because if you look at the energy of a certain charge distribution, whatever it is, and if the overall charge distribution is neutral, then it will have, depending on the center about which you find the multipoles, the energy of this charge distribution will be given by the minus d dot E term, and then there will be a quadratic term, and there will be this complete multipole expansion that you can look at, and then there will be other powers of E. So you look at, you have got the dipole moment d over here, alpha is the atomic polarizability, and this is the classical example, this is straight out of classical electrodynamics, and then you compare it with the result that you have just found in quantum mechanics. So this is exact, this is n not equal to 1, right, and this is exact. So here you have the unperturbed energy, the energy of the nth state will be given by the sum of the unperturbed energy plus the energy correction in the second order. The first order correction vanishes, and in the second order correction you have got a quadratic term in the amplitude of the electric intensity, and now you can compare the quadratic term, because a comparison of these two quadratic terms gives you the atomic polarizability. You can equate these two terms and you find that the atomic polarizability is given by the summation term that we just discussed. Okay? So from this you can also get the dipole moment, because it is proportional to the electric intensity through the atomic polarizability. So, now we had found that there is no Stark effect in the first order on the ground state. We found that the second order Stark effect on the ground state, it had a quadratic dependence on the electric intensity, and now we ask what happens to the excited states. Okay. Now we have to be a little careful, because once you go to the excited state like n equal to 2. So, let us take the first excited state of the hydrogen atom, and you know that the energy of the excited state will be given by with this 1 over n square formula for the hydrogen atom. But then you also know that these states are n square fold degenerate. Okay. This comes from the SO4 symmetry of the hydrogen atom. So, you do not have a unique eigenstate belonging to a given eigenvalue. Okay. You have more than one eigenfunctions, and in particular for n equal to 2 you have got the 2s and the 2p states, and the 2p state again is triply degenerate. So, you have a total of 4 degenerate states here for n equal to 2, and these 4 states are written out over here. So, for n equal to 2 you have 1 coming from L equal to 0, which is the 2s, and 3 coming from L equal to 1, which are the 2p states, with m equal to -1, 0 and +1. So, these are the 4 states, and all of those 4 states for r going from 1 to 3 4, they all belong to the same eigenvalue, which is the unperturbed eigenstate corresponding to n equal to 2. Okay. So, they are all degenerate. So, now you can ask the question that if you applied an electric field which was to remove this degeneracy, and now you switch off the electric field, to which of these states, to which of these 4 states will the perturbed wave function collapse into? You cannot get a unique answer, right, because there are 4 alternatives over there. So, you have to remember that all of these 4 states are orthogonal to each other, and they are also orthogonal to all the states for m not equal to 2. Okay. So, whenever m is not equal to 2 and I have an additional quantum number over here, an additional index s, because the m not equal to 2 state may also be degenerate, and if the degeneracy is md fold, then you will have 1, 2, 3 up to md linearly independent functions which belong to the same eigenvalue for m, right, for the mth state, and the n equal to 2 state is orthogonal to each one of them. So, this is the degeneracy of the mth state, and of course, these 4 states are orthogonal to each other within themselves. So, for r not equal to s, this projection, this inner product would vanish. Okay. So, we need to use what is called as the degenerate state perturbation theory in this case, and we will consider first order corrections to the n equal to 2, which is the first excited state of the hydrogen atom, using degenerate state perturbation theory. So, you have got these 4 states which are degenerate, and the perturbation is E times script E times Z. This is the charge, the script E is the electric field, and the perturbation order parameter is lambda. Lambda equal to 1 gives you the full Hamiltonian, lambda going to 0 will give you the unperturbed Hamiltonian, and now you can write the Schrodinger equation with the full Hamiltonian. So, this is H psi for n equal to 2, which includes the perturbation now, equal to E psi, and this E will be different from this E 0, and this Hamiltonian is this H 0 plus the perturbation. So, one might expect that this E, which is the eigenvalue of the full Hamiltonian, for different values of r may be different, but not necessarily so, because it depends on to what extent the degeneracy is removed by this perturbation. Okay. The degeneracy may be removed either partially or fully, and that is something that we will have to take into account. So, in this case in fact it will turn out that the degeneracy is not fully removed, but it is partially removed, and that is good because it reduces our problem considerably. So this is the Schrodinger equation with the full Hamiltonian, and we will expand the perturbed solution, the eigenstate of the perturbed Hamiltonian, as an expansion in the perturbation order parameter lambda. So you have got a term in lambda to the power 0 which will be the unperturbed state, but the unperturbed state is not unique, it will be a linear superposition of all the 4 eigenstates, right. And then you will have corrections in the first order, corrections in the second order, and so on, and typically lambda is a small tiny parameter, so you know the series can converge, hopefully, not that it always does. So this unperturbed part is a linear superposition of the 4 unperturbed eigenstates. We have already met them. These are the 4 linearly independent eigenfunctions which belong to the same eigenvalue of the hydrogen atom for n equal to 2. So this is n equal to 2, and S takes 4 values going from 1 through 4, and then these coefficients C we do not know yet, we will have to find a mechanism to determine these coefficients, which is part of this exercise, and this is the expansion for the wave function, and you have got a corresponding expansion also for the energy. This is the energy of including the perturbation. So it will be the unperturbed energy plus the correction in the first order, the correction in the second order, and so on, right. So this is the perturbation order expansion, and you have got similar relations for each value of r going from 1 through 4. Okay, so let us look at this wave function now, and this unperturbed part is a linear superposition of the 4 degenerate unperturbed eigenstates. Okay, it cannot be unique because there are 4 linearly independent functions, and these coefficients C are yet to be determined. So we now look at the first order correction. The first order wave function will again, because of the perturbation theory, we expect it to be written as a superposition of all the unperturbed states, okay, otherwise the perturbation theory will not work. So the perturbation theory works because of our contention that the perturbation is expressible in terms of superposition of the unperturbed states. So this is the superposition of all over all quantum numbers m of these unperturbed states, but for each value of m there may be d number of degenerate eigenstates, and we already know that there are n square fold, there is an n square fold degeneracy. So you must include a summation over all of these degenerate states. So the coefficient will therefore be indexed by r and also by m and s, okay, and this is the coefficient coming in the expansion for the perturbation solution for the n equal to 2. So I carried that index n equal to 2 as well. So the coefficient a here has got a number of indices over here, and all of them are important, okay, and I suppose that you have followed why each index is of significance. So this is of course the unperturbed eigenstate corresponding to the mth degenerate state, but the this depends on to what extent the level Em is degenerate, and this will again go as 1 over n square for n equal to m. So that is the degeneracy of the mth state, and now we can put all of these together by in the full Schrodinger equation, which is the full Hamiltonian operating on the full wave function, and this wave function is a linear superposition which is expanded in the perturbation order parameter. So you can substitute this expansion over here as well as on the left hand side as well as on the right hand side. The energy is similarly an expansion over the lambda parameter, which is the perturbation order parameter, and you can substitute this expansion over here, and the Hamiltonian itself is h0 plus lambda. So you have rewritten this Schrodinger equation for the full Hamiltonian, now using the lambda parameters, but now you know that all terms in corresponding powers of lambda must be equal. Okay. So, you can equate the terms for lambda equal to 0 on both sides of the equation to each other. Likewise, you can equate the terms in lambda equal to 1 on both sides to each other, and if you do that, then the coefficient of lambda equal to the coefficient of lambda which is equal to 0. So, from that you get this unperturbed solution, but the eigenstate is actually a superposition of these degenerate states, and the superposition consists of these coefficients CRS. Both R and S can take 4 values. You have got a similar relation for each value of R, but the summation is over 4 states. So, S will go from 1 through 4, and these are the coefficients to be determined. If you now do the same, equate the coefficients of the left hand side with the coefficients of lambda to the power 1 on both sides, left hand side as the right hand side, then you get H0, and then you have got lambda to the power 1 here on the left hand side, and then here is the term which has got lambda to the power 1. So, you have got H1 operating on this chi 0. So, these are the two terms that you get on the left hand side. On the right hand side, this is lambda to the power 0. So, you will have this term together with the term corresponding to lambda to the first power, which is this. So, you get E0 psi 1, and then you have the second term which is lambda 1, but lambda 1 and this term will give you the second power of lambda, that is a quadratic term, but in first order perturbation theory you will throw it. So, in the first order terms you will have only lambda 1, and this is lambda to the 0. So, you will get E1 chi 0, which is what you have over here. So, E1 chi 0. So, this is what you get on the right hand side. So, essentially what we are doing is first order perturbation theory of the degenerate state. Now, the first order correction we have seen is written as a superposition of all the unperturbed states. The superposition consists of the coefficients A for all values of m, which appears as an index m, but then it also must include summation over all the degenerate states which belong to the same eigenvalue for a given value of m. So, there is a summation over S going from 1 to the degeneracy of the mth state. So, there is an additional index m over here. Okay. So, this is the first order correction which we have found, and this unperturbed state is a superposition of all the degenerate unperturbed states corresponding to n equal to 2. So, now you can write this summation, this double summation over here, and this summation over here, and this whole equation can be rewritten with H0, and this psi 1, which is the first order correction, is written in terms of this expansion. So, that goes into this bracket, plus H1 operating on this chi 0, but chi 0 is this expansion over the 4 degenerate states. So, this is the chi 0 on the left hand side. On the right hand side you have got E0 psi 1. So, you have got E0 psi 1 is this expansion over m, and then the last term is E1 chi 0. So, which is an expansion over S. So, this is E1 chi 0. Okay. So, all we have done is to substitute the corresponding expansions. So, that is not really very difficult, and all we have done is to substitute these terms, and now notice that this H0 when it operates on psi 0 will give you E0 psi 0, and you have got similar terms on the right hand side as well, but which are the eigenvalues of the unperturbed Hamiltonian. But mind you, here the unperturbed eigenvalue is that corresponding to n equal to 2 state, whereas in this case this m will take the entire spectrum. Okay. So, you have to be careful about it, but then you have got similar expression in the first terms, and then you have got the remaining two terms, the second term on the left hand side and the second term on the right hand side, which has been written or rewritten just as it is. So, I take all the terms to the left and set everything equal to 0 instead of having a left hand side and a right hand side. I have taken all the terms on the right hand side to 0, change the sign. So, on the left hand side I will get this EM0 minus EN0 from the combination of these two, and on the right hand side I will get these coefficients are the same. So, it is summation over S going from 1 through 4 CRS, these coefficients are essentially the same in both, and then you will have H1 minus E1. So, this is just the perturbation correction, but this is the unperturbed Hamiltonian, which is this is the perturbation Hamiltonian, which is E times E, the script E times Z. Okay. So, this is the perturbation Hamiltonian. So, it is easier to look at this using the Dirac notation. So, this same expression has been rewritten here in the Dirac notation, and having written it in the Dirac notation over here, I take the projection for one of the 4 degenerate states of n equal to 2, any one, it does not matter which. So, I take the projection on one of them which is labeled as u, but then I can do it for all values of u going from 1 through 4. So, I know that u and s both go from 1, 2, 3 and 4, and when I take the projection, if you look at this term, in this, if m is equal to 2, if m is equal to 2, this difference in energy will vanish, and if m is not equal to 2, then this projection will vanish, because these states we know are orthogonal to each other. So, we do not get any contribution from this side when you take the projection, and then you are left with a system of linear homogeneous equations coming from here. So, you have got for every r a system of linear homogeneous equations, and there are 4 unknowns for every value of r, and this is the system of equations that we now want to solve. So, this is standard mathematical techniques which you are familiar with. So, this is how you solve the linear homogeneous equations. You know that non-trivial solutions will come for this condition. This is the condition that must be satisfied, that the determinant of this matrix would vanish, right. So, this is the condition to get non-trivial solutions, and the roots will give you the corrections, the energy corrections that you are looking for. Okay. So, these are the 4 roots that you are looking for. They may all be different from each other if the degeneracy is fully resolved. If not, some of them may be the same, or they may all be the same. So, you never know, right. But these are the solutions that you are looking for, and the degeneracy will be resolved if the Hamiltonian is perturbed, if the original Hamiltonian is perturbed, which has got a symmetry which is different from that of the original Hamiltonian. Okay. So, the residual degeneracy, there may be some, it can be either removed by higher order perturbations, or else it can even persist to all orders, and then you might want to, if you need to break it, you may have to use a different perturbation altogether. This particular perturbation will not do it. Okay. So, that depends on what is the symmetry of the perturbation Hamiltonian compared to the symmetry of the original Hamiltonian, as we have seen earlier, because degeneracy and symmetry goes together, and degeneracy can be broken only if you break the symmetry of the Hamiltonian. So, this is the system of equations that we want to solve, and the solutions are given by the roots of this equation. So, what you will do is, for each value of r, you can put, after you get the roots of the equation, you can put those roots and then get the coefficient c. So, now you know how to determine the coefficient c, because these were the undetermined factors which we had, but we have found a mechanism to determine this by plugging in the roots that you get, and for each root you can solve this set of equations, and from this set of equations you can get the corresponding coefficient CRS. So, that is a mechanism to get the solutions. So, let us illustrate this for a particular case. I will take the case of r equal to 2, just any one of those 4 values, and you take the root corresponding to r equal to 2, whatever it is, and then for each value of u going from 1, 2, 3 and 4, you will have 4 sets of equations. So, this is the equation for u equal to 1. So, all we have done over here is to put r equal to 2 and u equal to 1 in this, and then there are 4 terms coming in from here, and this is the 5th term. Okay. But this term has a Kronecker delta, delta us, so it will give you non-zero contribution only when u is equal to s. Okay. So, you will have a total of these 5 terms, and there is a similar set of terms for u equal to 2, a similar set of terms for u equal to 3, and a similar set of terms for u equal to 4. So, all you do is to substitute the different values of r, u and s. We are illustrating here this example for r equal to 2, and this is solving these equations will give you the coefficient c, and you notice that in this system of equations you have the matrix element of H1, which is the perturbation Hamiltonian, in the unperturbed states corresponding to n equal to 2, to all those 4 degenerate states. Okay. And you need to determine these matrix elements, and now you can put in the exact explicit expression for the perturbation Hamiltonian, which is this EEZ, and you have to get this. This is the overall integral that you must determine. So, this integration is a space integration over all values of r, theta and phi, phi going from 0 to 2 pi, theta going from 0 to pi, and r going from 0 to infinity. So, you separate the radial part and the angular part, carry out the integration. Here you have got z has got an angle dependent factor as well, because z is r cosine theta. So, z contains r as well as cosine theta, right. So, cos theta however is the Legendre polynomial for L equal to 1. So, you can put this spherical harmonic in this angular integration. So, you first carry out the angle integration over phi, but this is cosine theta for m equal to 0. So, which means that the only m quantum numbers which will come are those from this y l prime m prime and from y l m, because this has got L equal to 1 and m equal to 0. So, essentially in the phi integration you will have integration over phi of e to the I m prime minus m times phi. Okay. This is m prime and this is m. Okay. So, you get m prime minus I times phi, and this is non-zero only in the case that m is equal to m prime. So, that is the only case which is of interest, and that really offers tremendous advantage in our case. It also means that the degeneracy is not fully removed, and you will see this. So, we will discuss this from this point in the next class. I will conclude today's class by recognizing that the only terms which will give you non-zero value to this matrix element of the perturbation Hamiltonian are those corresponding to m equal to m prime. Okay. And you will remember that in the 4 degenerate states you have the 2s and the 2p. So, the 2p has got m quantum numbers going from -1 to +1. So, the terms corresponding to -1 and +1 will make no contribution, only the term corresponding to m equal to 0 will contribute. So, we will continue from this point in our next class. If there is any question, I will be happy to take. Yes.
Are we expressing perturbation in the eigenbasis of original Hamiltonian?
Yes.
So how is that symmetry difference between the original Hamiltonian and that perturbation Hamiltonian?
The symmetry of the perturbation is of course different from that of the unperturbed Hamiltonian. Okay? But the premise of perturbation theory is that whatever the perturbation does is expressible as a linear superposition of the unperturbed eigenstates. So, it is, there is no conflict in this at all. Perturbation theory works essentially on this basis that the perturbation does not throw the system outside its Hilbert space. Okay? The unperturbed Hamiltonian has got a certain Hilbert space. Okay? So, there is a certain basis, eigenbasis of the unperturbed Hamiltonian, and even after you impose the perturbation, the solutions will be expressible as a linear superposition of basis functions of the unperturbed Hamiltonian. That is the whole contention of the perturbation theory. That certainly does not mean that the perturbation has to have the symmetry of the Hamiltonian. As a matter of fact, if the perturbation does not have the symmetry of the Hamiltonian, it is not going to ever break the degeneracy. There is absolutely no conflict in this. The contention of perturbation theory is that the perturbation results in a new wave function which is nevertheless expressible as a superposition, as a linear superposition of eigenstates of the unperturbed Hamiltonian. So, whatever you do to the unperturbed Hamiltonian is not so wild that you cannot express the total wave function as a linear superposition of the unperturbed states. That is the whole premise of perturbation theory, and that does not require the symmetry of the perturbation to be the same of the as the symmetry of the unperturbed Hamiltonian. There is absolutely no such requirement. Why would there be such a requirement? The question of symmetry relates to a different aspect of this issue, which is the degeneracy of the state. Okay. So, the symmetry is important in the context of degeneracy, that if the perturbation has got a symmetry which is different from that of the symmetry of the original Hamiltonian, it would remove the degeneracy either partially or fully. Whether it does so fully or not depends on certain details, which is what we are examining over here. Like we have already seen that you get a non-zero connection between the states only if m is equal to m prime, not otherwise. So, m equal to -1 and +1 states of the two n equal to 2 quantum number. So, for n equal to 2, the non-relativistic hydrogen atom has got 4 degenerate states, right, and n square, which is the 2s and the 3 linearly independent eigenfunctions of 2p, which is for n equal to 2, l equal to 1, and m going from -1, 0 and +1. So, out of these 3, the m equal to -1 and +1 will not contribute anything to this matrix element. So, that is where the question of symmetry comes in, and it does not put any restriction on expanding the system eigenstate of the perturbed Hamiltonian, of the full Hamiltonian, as a linear superposition of the unperturbed states. In fact, that is the very premise of perturbation theory. Yeah. Any other question? Okay, so goodbye for now.